Welcome back to Sky Creative Channel. Join us as we explore cutting-edge construction techniques from America to Spain, Turkey to Japan, where modern technology meets timeless craftsmanship in road and rail construction. You know, watching modern road construction equipment work is like witnessing a perfectly choreographed ballet of steel and engineering precision. Take the VÖGELE Super 1900-3i and MT3000-2i pavers we're seeing here. These German-engineered marvels represent decades of innovation in asphalt paving technology, and they're changing how America builds its highways. NTHE Super 1900-3i comes equipped with what VÖGELE calls their fixed-width screed technology. Now, if you remember the old days of paving, you'd recall how difficult it was to maintain consistent mat thickness across wide highway lanes. This machine solves that age-old problem beautifully. The fixed-width screed maintains precise control over the asphalt mat, ensuring uniform density and smoothness from edge to edge. It's designed to handle paving widths up to 19 feet in a single pass. That's nearly 2 full highway lanes at once. What really sets these machines apart is the power feeder system. Think of it as the heart that keeps everything flowing smoothly. The power feeder uses intelligent sensors to monitor material flow constantly, automatically adjusting the feed rate to prevent any gaps or surges in the asphalt distribution. This means no more thin spots or thick patches that used to plague older paving operations. The augers distribute material evenly across the entire screed width, while hydraulic controls make micro adjustments dozens of times per second. NTH EMT 3000-2i model takes things even further with enhanced material handling capabilities. Its hopper can hold up to 15 tons of hot mix asphalt, and the conveyor system features what engineers call non-segregating technology. This prevents the larger aggregate stones from separating out, which used to cause weak spots in the pavement. The result? Roads that last 20 to 30 years instead of needing major repairs after just a decade. Both machines feature Ergo Plus operating systems, touchscreen controls that would look right at home in a modern aircraft cockpit. Operators can monitor screed temperature, material flow rates, paving speed, and mat thickness, all from one central display. The technology even includes automatic grade and slope control using laser or sonic sensors to follow predetermined road profiles with millimeter accuracy. High-speed rail construction represents one of the most ambitious engineering challenges of our modern era, and what Ferrovial accomplished on the Madrid-Galicia line's Old Meadow to Petrol Bar segment showcases the pinnacle of railway construction innovation. This isn't your grandfather's railroad building. This is precision engineering at speeds that would have seemed impossible just a generation ago. NTHE process begins with sleeper delivery. These aren't the wooden ties many of us remember from childhood railroad crossings. These are pre-stressed concrete sleepers, delivered in bundles of 7 along each side of the prepared track bed. Before a single sleeper touches the ground, Ferrovial's crews lay down the ballast foundation using a systematic approach that ensures stability for trains traveling at nearly 200 miles per hour. NTHE ballast material itself, crushed granite stone, carefully graded for size and angularity, gets spread by specialized machines, then compacted using vibrating plates. Here's where Ferrovial's innovation shines. They create a longitudinal groove along the center line before placing sleepers. This prevents center loading damage, a problem that plagued earlier high-speed rail attempts. Next comes hydraulic sleeper placement. Automated equipment positions each sleeper exactly 60 centimeters apart, about 24 inches for those of us who grew up with imperial measurements. This precision matters tremendously at high speeds, where even slight irregularities can cause dangerous vibrations. NTHE rail installation process is genuinely remarkable. These aren't short rail segments like traditional railways used. We're talking about continuous welded rails in 270-meter sections, nearly 3 football fields long. Ferrovial developed a proprietary system using rollers, flanges, and specialized bulldozer-drawn equipment to lift these massive rail sections from storage racks onto the prepared sleeper bed. Their patented squaring machinery then ensures perfect alignment. And according to Ferrovial specifications, their system can install, square, and anchor approximately 4,500 meters of single track daily. That's nearly 3 miles of precision railway every working day. The anchoring process uses computer-controlled torque wrenches to fasten each rail clip to exact specifications, ensuring consistent holding force across thousands of connection points. And after initial rail placement comes ballast addition and preliminary compaction, using heavy machinery to achieve what engineers call pre-handover condition. Then the truly specialized work begins. Aluminothermic welding joins rail sections using molten metal that bonds the steel at a molecular level, creating essentially one continuous rail stretching for miles. NTHE final stages include comprehensive compaction, neutralization to eliminate thermal stress, final sweeping, and precise shaping of ballast edges and track gauge. It's this attention to detail that allows modern high-speed trains to glide smoothly at speeds that would have amazed railway pioneers like George Stephenson or Cornelius Vanderbilt. Japan has always held a special place in the world of infrastructure engineering, and the Isahaya Outer Circular Route project exemplifies the meticulous precision and innovative thinking that Japanese construction has become famous for worldwide. Built by the MMB/Yoshikawa joint venture, this project represents modern roadway construction at its finest, combining traditional Japanese attention to detail with cutting-edge technology. What makes this project particularly interesting is how the joint venture approached the challenging terrain. Isahaya sits in a valley with surrounding hills, meaning significant earthwork was required. The excavation phase employed GPS-guided bulldozers and excavators, technology that would have seemed like science fiction to the road builders of the 1960s and 70s. These machines use satellite positioning accurate to within 2 centimeters, allowing operators to cut and fill to precise grade specifications without constant surveying. NTHE's soil management aspect deserves special attention. Japanese construction standards are notoriously strict about soil compaction and stability. Every layer of fill material gets tested for density and moisture content. The compaction equipment used here includes intelligent soil compactors with built-in measurement systems. These machines use vibration analysis to determine when the soil has reached optimal density. They literally feel when the ground is properly compacted, adjusting their operation automatically. And foundation preparation for this route involves stabilizing soft alluvial soils, common in lowland areas. The construction team used cement mix soil improvement techniques, where specialized machines inject and mix cement slurry into the native soil, creating columns of stabilized material that support the roadway structure above. This method has been refined in Japan over decades and prevents the settlement issues that plague highways built on soft ground. NTHE drainage system design reflects generations of Japanese experience with heavy rainfall. Isahaya receives over 80 inches of rain annually, more than twice what Seattle gets. The roadway includes sophisticated subsurface drainage with perforated pipes, graded gravel layers, and carefully engineered collection systems. Storm drains connect to retention basins designed to handle the intense rainfall of typhoon season without overwhelming local waterways. NBASE course construction utilized locally sourced aggregate materials, processed to exact specifications for gradation and cleanliness. The crushing and screening plants operated near the site, reducing transportation costs and environmental impact. Multiple lifts of base material were placed and compacted, with each layer tested before the next was added. This systematic approach ensures the pavement structure will support heavy truck traffic for decades. NTHE asphalt paving operation employed state-of-the-art machinery, similar to what we saw earlier, but adapted for Japanese specifications. Japanese asphalt mixes often include polymer modifications that improve durability in the country's variable climate, from hot, humid summers to cold, snowy winters in some regions. The paving train worked with military precision. Material delivery trucks fed the paver continuously, while multiple rollers followed in sequence to achieve the specified density. Quality control throughout this project was exhaustive. Japanese construction contracts typically require far more testing than Western standards. Core samples, density measurements, smoothness readings using laser profilers, and friction testing ensure every meter of pavement meets stringent specifications. This attention to quality is why Japanese highways often last 30 years or more with minimal maintenance. NTHE project also incorporated modern safety features we've come to expect in 21st century highway design. Wide shoulders for emergency stops, gentle curve radii for safe high-speed travel, proper sight distances at intersections, and LED lighting that's energy efficient yet provides excellent visibility at night. There's something deeply impressive about watching massive, pre-stressed concrete beams being lifted into place on a highway viaduct. The Barranco de Zacatin project on Spain's A7 Mediterranean highway represents modern bridge construction at its most dramatic, where engineering calculations meet real-world execution in spectacular fashion. NNTHE beam installation process begins long before crane day. Pre-stressed concrete technology, developed extensively in the 1950s and 60s, involves embedding high-strength steel cables in the concrete and tensioning them before the concrete fully cures. This creates compression forces that counteract the tension forces the beam will experience when supporting highway traffic. It's brilliant engineering. The beam is literally preloaded to handle stress. These particular DT-type beams feature a distinctive double T cross-section that maximizes strength while minimizing weight. The wide top flange provides ample surface area for the bridge deck, while the vertical web and bottom flange create structural depth for spanning the ravine. Manufacturing these beams requires specialized casting beds where the pre-stressing cables are stretched to tremendous tension, often 180,000 pounds per square inch, before concrete is poured around them. End crane selection for this operation is critical. The equipment you're seeing is likely a large mobile crane with capacity exceeding 100 tons, positioned carefully on prepared pads to distribute ground pressure. Riggers attach specialized lifting slings to embedded steel loops cast into the beam tops. Him placement requires extraordinary precision. The beam ends must land on bearing pads, positioned atop concrete pier caps. These elastomeric bearing pads, typically made of reinforced rubber, allow slight movement for thermal expansion while transferring the bridge load to the piers below. Once beams are positioned, construction crews install transverse diaphragms between them for lateral stability, then build a concrete deck that forms the actual driving surface. The deck concrete bonds with the beam tops, creating a composite structure that's stronger than the sum of its parts, a principle engineers call monolithic behavior. Interstate highway reconstruction represents one of the most challenging tasks in American civil engineering. The I-57 widening project executed by Simonds Construction perfectly demonstrates the complexity of expanding existing highways from 2 lanes to 3 while maintaining traffic flow and meeting modern pavement standards. This is American infrastructure renewal at work. NNTHE reconstruction process begins with pavement removal. Specialized milling machines grind away the old concrete surface, which gets crushed and recycled as base material. It's satisfying knowing that highways being rebuilt today incorporate materials from the original construction. Connecting past to present, NTHE foundation work is crucial. E.T. Simonds. Crews first established precise grade and alignment using GPS survey equipment tied to permanent benchmark stations. String lines and grade stakes guide every subsequent operation. Where soft subgrade soils exist, stabilization treatments using lime or cement ensure the foundation won't settle over time. End-chair placement and reinforcing steel installation represent the heart of concrete pavement construction. The chairs are small plastic or metal supports that hold steel reinforcement bars at the proper elevation within the concrete slab. These rebars, typically half-inch to 3/4-inch diameter steel in a grid pattern with 12 to 15-inch spacing, provide tensile strength that prevents cracking as the pavement expands and contracts with temperature changes. Rebar work is physically demanding and requires precision. Steel workers cut bars to exact lengths, tie them together with wire at intersections, and verify proper spacing using templates. The steel must be positioned carefully, too close to the surface, and it won't provide adequate structural benefit, too deep, and it leaves the upper portion of the slab vulnerable to cracking. Experienced ironworkers can place and tie hundreds of intersections per day. End concrete placement is where everything comes together. Ready-mix trucks deliver specially formulated paving concrete with exact slump, air content, and strength characteristics specified by highway engineers. Modern concrete pavers receive this material through a spread hopper, distributing it evenly across the lane width. The paving machine moves forward steadily, typically at speeds around 4 to 8 feet per minute, while vibrators consolidate the concrete and screeds strike it off to precise elevation. Once mixed, concrete begins its chemical curing process immediately. Construction crews have perhaps 90 minutes to place, consolidate, finish, and texture the surface before the concrete becomes too stiff to work. NNTHE curing process is critical. Fresh concrete must be kept moist for several days while it gains strength. Crews apply liquid membrane curing compounds that seal the surface, preventing premature moisture loss that would compromise strength and durability. In hot weather, wet burlap or continuous water spray may be necessary to prevent thermal cracking, NET. Simonds, systematic approach to this I-57 widening, working lane by lane, maintaining traffic flow on adjacent sections, coordinating utility relocations and drainage improvements simultaneously, exemplifies modern reconstruction methodology. It's not as simple as building new highway on virgin ground. It's surgery on an active transportation artery, requiring planning, patience, and precision. The result will be a highway segment ready to serve travelers. The Gebze-Orhangazi-Izmir Highway stands as one of Turkey's most ambitious infrastructure projects, and watching its construction unfold reveals the enormous scale and complexity of modern highway engineering. This isn't just road building, it's transforming an entire region's transportation network, connecting Istanbul to Turkey's Aegean coast with world-class infrastructure. What makes this project particularly impressive is the challenging geography. The route traverses diverse terrain from sea-level coastal plains near Istanbul to mountainous regions inland, requiring massive earthwork operations. Modern GPS-equipped earth-moving equipment makes this possible on an unprecedented scale. Excavators and bulldozers, working in coordinated fleets, can move millions of cubic meters of earth, cutting through ridges and filling valleys to maintain consistent highway grades. NTHE earthwork operation alone employs hundreds of pieces of equipment. Giant articulated dump trucks, each carrying 40 to 50 tons of material, run continuous cycles between cut and fill areas. Scrapers, those ingenious machines that can cut, carry, and spread earth in one operation, work the longer hauls. Compaction equipment follows, including sheep's foot rollers for clay soils and smooth drum vibratory rollers for granular materials. Every lift of fill material gets tested and verified before the next layer goes down. NNBASE coarse construction at this scale requires dedicated aggregate production facilities. Crushing plants process quarried stone into specified gradations, screening and washing to remove clay and organic materials. Quality control laboratories test samples continuously, ensuring every truckload meets specifications for size, cleanliness, and strength. The processed aggregate gets stockpiled by type, then drawn down as paving operations progress. Northern Bridge construction along the route showcases multiple modern techniques. Shorter spans use precast concrete beams, similar to what we saw in the Spanish project. Longer spans employ cast-in-place concrete with elaborate falsework supporting formwork until the concrete cures. The most dramatic crossings use segmental construction, where bridge decks grow outward from piers and balanced cantilevers, with pre-stressed cables providing structural continuity. Asphalt paving operations for a project this size are industrial-scale productions. Multiple asphalt plants operate along the route, producing thousands of tons of hot mix daily. Paving trains work multiple shifts, placing base and surface courses in continuous operations that can pave several miles per day. Quality control is relentless. Density testing, smoothness measurements, and material sampling ensure every segment meets international highway standards. NNTHE Gebze-Orhangazi Izmir Highway includes another marvel deserving mention, the Osman Gazi Bridge spanning the Gulf of Izmir. At the time of its completion, this suspension bridge ranked among the longest in the world, with a main span exceeding a mile. Its construction alone represents a multi-year engineering feat involving foundation caissons sunk to bedrock underwater, massive concrete towers rising nearly 500 feet, and miles of steel cable.